In this video, I introduce latent diffusion planning for imitation learning. Latent diffusion planning is a modular latent planning approach, which learns a planner that can be trained on action-free data and inverse dynamics model that can be trained on possible suboptimal data. LDP further trains a variation autoencoder with a reconstruction loss to produce compact latent embeddings that are used by the planner and IDM. As we hear, this is the architecture of a variational autoencoder. Then LDP learns imitation learning policy through two modules. One, a planner that consumes demonstration state sequences without action involved. As shown here, this is a planner which uses output from the trained encoder as an input. Two, IDM that trained on in-domain, possibly suboptimal environment interactions, as shown here. Both of them rely on denoising diffusion probabilistic model, as shown here. To train a VAE with encoder Q5 and decoder P theta, the beta VAE objective is defined as here and explained in this figure. Where X is an input image, Z is a learned latent representation of the image X, theta is the parameters of the decoder, and phi is the parameters of the encoder. Latent diffusion planning for control planning consists of three parts. One, an image encoder is trained using VAE via reconstruction loss. And two, a planner is trained to forecast the future latent sequence, Z carriage, using planner loss. Three, IDM is trained to extract the control action AT from pairs of the latent states ZT, ZT plus 1 using inverse diffusion dynamics loss. The planner is the condition on the latent embedding generated by the trained encoder, which consists of the concatenation of the latent image embedding and robot proprioception and diffuse over the horizon of future embeddings. The planar diffusion objective is defined as here, where E psi is the planar, psi is the parameters of the planar diffusion model. Zk is the latent embedding at time step k of the trajectory. Zk plus 1 caret to Zk plus H caret are the noise latent embedding sequence with the corresponding noise E. H is the maximum horizon of the forecasted latent plane, and T is the diffusion noise step. This is the inverse dynamics model, and this is the latent planar model. IDM is trained to reconstruct the action between a pair of state conditions their associated latent embeddings. The inverse diffusion dynamics loss is defined as here. Where E she is the IDM, she is the parameters of the inverse diffusion dynamics model. Zk is the latent embedding at time step k of the trajectory. AK caret is noise the action. At inference time, the planner and the IDM are combined to extract the action sequence. Pseudocode of the LDP is shown here. First, the planner predicts the future embeddings via DDPM sampling. As we observe initial state x0 and image x0. Then we calculate the embedding using the encoder E. And then we do the planning in the latent space, get the future latent embeddings, Z caret as shown here. Then IDM extract the action from latent embedding pairs produced by the planner, as shown here. This is the extracted actions. Finally, LDP executes the extracted actions to generate the future state, as shown here. This is the future state. For more details, please check with these references. Thank you. Bye.